Ben diğer bilgisayardan geçiş yapsam daha iyi olur. Kapatıp geliyorum 2 dakikaya.
Tamam.
Sıkıntı var.
Sesim geliyor mu şu anda?
Duyuyorum hocam.
Tamam, süper. Diğer bilgisayarda sıkıntı oldu da başka bilgisayara geçtim. Okay, I have just started recording. Hello everyone again. As you know, in the framework of this manufacturing processes class, we finished casting part, and now we will investigate and talk about the plastic deformation or metal forming processes. And today we have a guest, we have a special guest who is Mert Aygen from NETFORM Engineering or NETFORM Metal, if I am wrong, and I'm sure our guest will actually correct me. I hope all you will enjoy this lesson and you will have some benefits in terms of the industrial perspective and what's going on in industrial actually site. By the way, I would like to take this opportunity to thank Mr. Aygen for his kindness, for inviting, actually for accepting our invitation. So that's why on behalf of my department and my university, again, I would like to thank him. Thank you very much, Mr. Aygen. And actually, I briefly introduce you, and I am sure also you will introduce yourself and your company and so on. Okay, stage is yours and microphone is yours.
Okay, thank you very much for this nice and kind introduction about me and my company, and thank you very much also for inviting us as a guest speaker in your course. So I hope this will be a beneficial presentation and lesson for the participants and the students. And I will try to do my best, to give some insight into the theory behind metal forming and plasticity. And then I will try to give some information about the real-life industrial applications regarding metal forming. So if you look at the content of this lesson, I will just briefly talk a little bit about us, who we are, and then I will move to what deformation is, and I will try to, maybe you have seen in previous lectures before about the stresses and strains, so it might be a reminder for everybody. And then I will move to manufacturing methods and then types of metal forming, and I will show some application examples, and at the end I will be with you for 2 weeks, I mean this week and next week, and show like a teaser a little bit about what we are going to talk about in the next lesson. And I will take some short breaks while changing sections to get some questions, because I don't want to accumulate all the questions till the end. And then maybe halfway through, like in 40 minutes maybe, we can take a 10-minute break to get some fresh air and refresh our coffees and teas, if it is okay for everybody. I would like to start with who we are. My name is Mert Aygen. I'm a co-founder of NETFORM Engineering, and it is actually machinery and metal. You are right. But we are mostly focusing on the engineering part because we don't have a production facility, at least for now. And as you can see the timeline here, we started our adventure, at least I started my adventure in mechanical engineering in 2000 and finished my undergraduate and graduate studies in mechanical engineering department of Üniversitesi Technical University, and then started working at Norm Fasteners, which is also located in İzmir, and at the moment they are the biggest fastener producer in Turkey and worldwide. As far as I know, they are in top 5, if I'm not wrong. And I studied there as an R&D engineer. I was responsible for tool design and finite element simulations of forging, cold forging processes, and also cold forging tools. In 2007, I decided to take a step forward and moved to Denmark to a company. It was a small company with 15 people, which has a niche, special patented technology to produce cold forging tools. And I worked there as also a design and simulation engineer for 3 years. And in 2010, we decided to try something new and started our own engineering company. As you can see here from the news, it was very well received by COSGAP because, you know, we are complaining about this brain immigration, and it was for COSGAP, it was a very good opportunity to bring some brains back to Turkey. So they accepted our R&D project, and then we got a funding for our startup. And then in 2010, we started our small company. And then, as you can see here, after 3 years, we finalized our prototype adjustable forging die, which was working with 1,000 bars internal pressure, and it was ready to present, and we successfully finished that project. But unfortunately, it remained only as a we couldn't sell it or just move to mass production because of some bulky sizes and so on. I mean, it didn't go as planned, but at the end, we had a successful system. But during the last 10 years, we start to serve a broad area related to production. We are mostly focusing on metal forming. Of course, we are coming from cold forging, and we have a hands-on experience with that type of process. But on top of cold forging, now we are working on warm and hot forging, sheet metal forming, roll forming, and in addition to the metal forming, we are also taking parts in the projects about welding, mechanical joining, additive manufacturing, and also we can develop some optical control systems by using the machine vision technology. So we are located in İzmir. At the moment, unfortunately, our office is closed because our office was located in the middle of Manavkuyu, Bayraklı. And now more or less all our neighbor buildings are being demolished because they were heavily damaged during the earthquake. So now we are closed for maybe a couple of weeks, then we will get back home. We take or give services in different categories. We just split them in 4 different segments. We are acting as a representative of some products like forging tools or some forging presses. But the main area where we spend our time is the simulation softwares. We are both giving services as engineering studies and we also, sell this software who wants to integrate this technology into their own company. And we give also some additional services like material testing, tool design, tool life improvement, process design, and software development related to machine vision or image processing. And as the last product or service segment, we are also giving trainings for both software and also for tool design and metal forming process development. And at the moment, maybe you may recognize some of the companies here. We are working with several companies in automotive industry and defense and aviation. I will tell a few things later about some trending topics in production area, addition to metal forming. And last but not least, we are also trying to keep contact with universities because we believe it's extremely important to improve technology in our country and to be able to apply advanced engineering capabilities or to be able to produce new high-tech, advanced and high-end products. It's a must to have a good process regarding research and development. And since companies cannot do it on their own, it is extremely important, it's crucial to have a tight cooperation with universities. And I want to take this chance to thank İYTE for inviting us again for this event. So if we go back to our subject, before we talk about metal forming, we should understand what deformation is. Deformation, this dictionary, of course, explanation, change in shape or size of an object under a certain stress. I think it is quite clear and everybody knows more or less what deformation is. And this deformation can happen in two different ways in a material. The basic two categories or two definitions we have here is elastic deformation and plastic deformation. Elastic is a temporary shape change, which means that once the stress acting on a material is removed, this material or body gets back to its original shape. And that is why I added a spring here. So material works basically like a spring, as an ideal spring, that it remains its shape. Plastic deformation, on the other hand, is completely opposite. And here we get a permanent shape change under a certain stress or loading. And now when we have plastic deformation, the shape change is more or less can be named irreversible. Of course, there's a little bit of spring back, which reverses the deformation, but it's a marginal amount. But if you look at the main result, it's a kind of one-way ticket. So, I mean, once you have this plastic deformation, you change the microstructural condition of the material, and you have a newer shape than the original one. So, very, very simple, basic example is, tensile testing. If you look at the specimen, if you just pull it up to the point it fractures, you will see a certain amount of necking, a reduction in the diameter of the specimen, which is a clear example of plastic deformation. When we talk about deformation, there are two terms that we should be familiar with. The first one is strain. With a lean explanation, I can say strain is the relative deformation of a material under applied forces. This can be elongation or compression, doesn't matter. But if we just take a steel bar or just a rod, and if we just pull it from two sides, we will clearly see a certain amount of length change, which can be designated as delta L. And the ratio of this delta L to the original length gives us the relative deformation on this part. So we just call this strain. Stress is sometimes, at least in industry, we see that it is mixed up with force, and different or wrong units are being used, like, oh, we have a stress of 10 tons, or we have a force of 100 megapascals. So these are completely different things, even though they are linked to the same physical phenomenon. Basically, stress is force per unit area. So and stress is also a tensor, which means it is both a scalar value and the direction. When we look at the stresses on a material, we can also split this term into two, which can be named as axial and transverse stresses. So it depends on the direction which these stresses are acting on the body. And these stresses result in different types of deformation. So under axial or normal load, which can be named as force or stress, this load is acting perpendicular to the surface of the body. So it is, head-to-head interaction. So under this kind of loading, we see either tension or compression. If load is acting parallel to the surface, then we call this shear, like cutting. Cutting is also a type of shear, but happening. I mean, if you take a scissors and if you just zoom in to the cutting edge, there we see this shear effect. So in that kind of process or under loading condition, the forces or stresses acting parallel to the surface of the body. So I give this metrobus example, the ones that we have in Istanbul. If you just take the people inside this metrobus as atoms in a material, that is very similar to a material. It's of course, I'm not a material or metallurgical engineer, but this is a very macro scale example to just imagine what is going on in the material. So to be able to deform something, like getting more people in the bus, people should sleep on top of each other, and this is also how particles inside the material are moving. And once we have this movement, we have a little bit of shape change. If one person moves to the other side of the other person, then we can call this a permanent shape change. So because people are changing location, they are dislocating, moving to a new position, and they cannot come back. But if there's only a slight pressure on top of each other, so there will be no permanent change of the position of the people. And once the doors of the metrobus is shut, and there will be a release, people just get back to their original position. So you can just imagine this as a spring back. So atoms inside the material are acting in a very similar way. I'll use this example later while talking about deformation rate. because I think it is still a nice way to depict or visualize this molecular interaction in a material. There are a few more things that I want to talk about before we move on and talk about the real production, because we should first understand what is going on with the material and how it can be different from one material to another. So there are different terms that we use when it comes to metal forming. First, we should understand a little bit what this stress-strain curve is. This curve shows us the behavior of the material once we go beyond the yield stress of that material, which means when we have this permanent shape change, this graph or diagram shows how much it will harden, get stronger when we deform it more and more. I intentionally put this graph here because it shows a clear difference between engineering stress strain curves and true stress strain curves. And lots of people just mix them up or even don't know about what true stress and strain curve is in industry, because since we are being involved in lots of different projects, we saw that engineers mostly focusing on engineering stress strain curves. I don't say it is useless. It has some purpose. It helps us to categorize the material, to identify how ductile it is, what yield stress is, and how much it can, elongate and so on. But still, it is not sufficient to explain formability or forming behavior of the material. I will not go deeper in this subject, but if you have any questions, I can explain more about it. But the thing is that, because next lesson we will talk about numerical simulations, there we should define the material and its properties, especially this flow curve, we call this flow curve, by using true stress strain curves. Another way we distinguish materials is whether they are ductile or brittle. Two different materials, they may have same yield stress, which means that they will start changing shape permanently at the same level. But the shape change which they can take or bear till fracture determines how much we can form them, how much we can shape them. And if material deforms relatively more than the other one, we call them ductile material, which means that we can cause a clear shape change on the material until it ruptures or falls apart. However, with the brittle materials, we can barely change the shape. So it will just deform a little bit, and then it will fracture or rupture all of a sudden, like a glass, which is a quite popular brittle material. And if you look at aluminium, for instance, which is quite ductile, it takes some time and deformation until you can break it, for instance. So these two terms is also extremely important for us. Ductility comes into play when we talk about materials that we are going to form and produce parts with, and brittle materials are mainly a subject of tools which we use to form the parts. And here again on these two graphs you will see a definition called strain hardening. We talk about yield stress of a material, let's say 300 megapascal, and we start changing its shape. We basically pull it from two ends, and then we pass the yield stress, which means the force over area. And once we start deforming it beyond the yield stress, it will get harder, and it will increase its strength, and at the same time it will be more difficult to deform it further. We call this hardening. So the more you deform the part, the harder it will get. The reason why there is strain hardening, strain in front of the hardening word, this hardening here, the one that I'm talking about, is based on the shape change. I will only use this in one sentence here, and I'm not go deeper in the subject because it's quite complicated. There's a different type of hardening, which is called kinematic hardening. And that hardening occurs when you change the direction of the load, which means if you pull something and then push and then pull again and then push, during the cyclic loading, material will undergo a different type of hardening, which is called kinematic hardening. But in metal forming, we mostly face with the strain hardening phenomenon. And in very rare processes, like sheet straightening or spinning, we have to take into account kinematic hardening behavior of the material. I know this theory things are quite boring. And when I was also a student, I was asking, okay, where I'm going to use this. But believe me, when you start to analyze something, or when you try to solve a problem in real life, you should act like a doctor. And as a doctor, you should know the anatomy of the body. Here we are talking about the material, and we should know what is going inside the material to able to give answers to the questions. So now some real world photos, and to make it more understandable hopefully. So we have this two worlds, elastic world and the plastic world. When we design a system or component or something like an engine or some drivetrain in a car or car body, something like that, a working system, we try to stay in the elastic region. So we don't want anything in this huge engine to change shape permanently. So what we want, when we stop the car, we want everything go back to its original position. If something changes shape permanently, then there's something wrong there, and which is taken as a failure in the system. However, on the right side, when we try to produce a part by shaping it, by forming it, then we should definitely go beyond yield stress, which is the plastic world or plastic deformation. Because if we cannot go beyond the beyond yield stress, once we remove the load, raw material will go back to its original state, and we will not be able to produce anything. So that is the biggest difference we see here while designing a part and then producing a part. For instance, this part here at the top is an example of hot forging, and it is a connecting rod in this engine. Maybe not in that engine, but this is what we have in the cars and in all internal combustion engines today. Not talking about electric cars, of course. But when we design it, we define the loads and design the part in a way that we should be able to bear that load, and the stresses remain below Y here. Y is the yield point. There are some other definitions here, like proportionality limit or elastic limit, but what we take as the critical value or threshold is the yield point. But once we want to produce that connecting rod, we design a process where just we go beyond yield stress and change its shape permanently. And the other examples, these are the cold forged parts, and these are sheet parts, and everything is done in the plastic zone here. And I will name two different words that we also often use in numerical simulation. It is linear analysis and non-linear analysis. When you talk about the elastic deformation, if we just ignore these two small sections, the non-linear curved part, elastic deformation for metals is assumed to be completely linear. So that is why in a CAD software, it's quite easy to perform a simulation of a body like a connecting rod. You just fix and you apply some forces, and in 10 seconds, you get a result, some nice colorful pictures showing the deformations and stresses. However, for plastic deformation, things are a little bit more complicated, because now we don't have a linear relationship between the deformation and the stresses. Therefore, we need to go step by step with small calculation steps, which is more time consuming, of course, and that is why you should use some nonlinear solvers or simulation programs to be able to analyze metal forming process. We will talk about more in the next lesson, next Friday. So, do you have any questions up to this point about what stress and strain is, what deformation is, linear, non-linear, elastic deformation, plastic deformation, and so on? If any questions, please feel free to barge in and say something, comment on it, or just raise a question. Anything? I hope everybody is there. Okay, then, if there are no questions, I will continue. There are different types of manufacturing methods, and it's not possible to say this is the best, this is the worst, and so on. Everything has a role, everything has a purpose, but sometimes we can have more than one option to produce a part. For instance, if we look at this drawing here, this is the shaft or part with two different diameters and a conical transition area. And we can basically produce it in four different ways. One is, casting. You can just melt the raw material and put it in a mold and then let it solidify, and then you will get the part. The other one is metal forming, where you put the raw material in a die and use a press to shape it. We can machine it, which is extremely popular and handy process. So we can just take a big chunk of material and then remove some of it and get the final part. Of course, there will be some waste. And we can weld it. Take two different bodies as two different sections of the final part, and we can put them together with welding. It can be arc welding, laser welding, resistance spot welding, friction welding, whatever it is. But there are some pros and cons of these production methods. And metal forming will be the most feasible way to produce a part. Here on the upper right picture, we can see a much more complicated shape here with the hexagonal head, and then there's a shoulder step here, and we can see it is hollow inside. So what we can do, we can just take a hexagonal raw material, put it on a CNC lathe, and machine it. But what will happen? We will just throw away 2/4 of the material. So it will be quite costly. But if we forge it, if we just form it in a cold condition, then we will use a much smaller material, and we will only throw away 6% of it because we need to make a hole inside. And this will be the tiny scrap that we will have at the end of the process. And just imagine if you have to produce 1 million parts of this example, then you will lose quite a bit of money if you throw away more than 70% of the material. And if you look at the production times, this may take maybe up to 5 minutes or something like that, and you will be able to force this maybe 3 or 4 steps, 1 second for each step, and then you will it may take 5, at most 10 seconds to produce this part on a cold forging machine. On top of that, you may need some criteria about the performance. And if you look at the metal parts, they are mostly working in some harsh environment, and they are subjected to cyclic loading, which brings the failure mode called fatigue into play. Fatigue is a very critical subject, which determines the life of a component, especially in a system where things are rotating or as I said, subjected to cyclic loads like tension, compression, and so on. And their microstructure of the material plays an important role in fatigue life. If you look at the lower right picture, you will see the grain distribution in a material with the same shape, but the difference is that left one is machined from a bigger round material. So you can see this part is cut away, which made these grains just open to the free air. And I don't have that picture here, but if you just zoom in there, we will see lots of tiny cracks on the surface. In the other one, which shows the part produced by forming it, we see these grains follow a path parallel to the surface. Therefore, flows or these tiny cracks are much less on this part compared to the other, which was machined. And what we know in fatigue is triggered by the small cracks that we have on the part, and these cracks starts to propagate. They start to get bigger till part fractures. So the less cracks that we have on the surface of a part, the higher the fatigue life will be. So this is why we get a much better grain flow in a part which is formed compared to the one which is machined. And if we consider casting is much worse because we have porosity, some small holes in the part, which is a little bit of inevitable. It can be minimized. There are some advanced casting equipments where we can lower this flows inside the material, but still compared to the forming, still the performance of a cast part will be more or less, or in most cases, less than the formed part. So I'm of course generalizing this statement. There might be some exceptional cases where a special casting technique is used, or a special surface finish technique is used on a machine part, which can improve the life of those parts. But in the raw condition, when we have this head-to-head comparison, in majority of the cases, forged parts will show a better fatigue life. So if we summarize these things as the advantages of metal forming, we are talking about high material utilization, which means very low or zero scrap or waste. High production speed, because these presses are working at a very high speed, so forming operation can take from half second to 1 second or 2 seconds. In most cases, if you are using a mechanical press. On hydraulic presses, it may take maybe a couple of more seconds, but still a shorter time compared to casting or machining. High dimensional accuracy, especially if we are talking about cold forging, we will get very tight tolerances on the part, if of course the tool design is done correctly. And as we talk, high fatigue life will be higher with formed parts. This is like an intrusion to this presentation, but I just didn't want to go on without saying a few words about this TT. Probably the new generation is using this more than I do. Trending topic, it is additive manufacturing. So here in this example, we talk about the 4 main conventional manufacturing methods. But believe me, we will talk more and more about this method in the future. This is also which is known as 3D printing. It is broadly used in medical applications and becoming more and more popular in aviation, aerospace, and defense. Not in automotive that much because the production speed is low and it is still costly. So still in Formula 1 cars, you may see some 3D printed parts, but not in Ford Focus or something like that. The conventional cars that we are using today, it still needs some time to get that point. And if you look at the tweets of Elon Musk from 2013, they've been using this technology for a while, you know, in their SpaceX rockets. So, and in the future, you know, when you go somewhere, you should take spare parts with you in case something gets broken. But if you go to Mars or somewhere further, you will not be able to carry luggages, suitcases full of spare parts like bearings, shafts, bolts, nuts, whatever. So we should pack lightly. So the idea behind, the motivation behind is using this technology. Just take the machine or this printer with you and print whatever you need there. So this is a rival of metal forming, but still strong enough to compete in terms of financial matters, because still this is a very costly technology. But it is getting cheaper and cheaper with new machine producers and newer machines where you can speed up the process and where you can produce several parts at once, because 10 years back you could only produce one part at a time. So now you can make them in small batches, like 50 or 100 parts if they are small at once. So cost per part is getting lower and lower every day. Maybe we can take a 10-minute break and continue at 4:30. If it is okay for everybody, then I will show some examples of bulk metal forming and sheet metal forming.
Can I ask a question?
Sure, please.
You have said that the cost of 3D printers decreased very well. Am I wrong? Sorry.
Yeah, it is. I mean, compared to 5 or 10 years back, it is more at a reasonable level.
So, do you think that the costs are going to decrease in the future as well?
Yeah, definitely, because.
Or did we come to limitations?
No, I mean, depends on the type of the process. I mean, if you are talking about the powder bed, yeah, there will be some limitations regarding the laser power and the build space. But there are now new technologies like binder jetting. And that technology is quite suitable for large batch sizes of small parts. And there, you basically don't melt anything. You just compact them with a binder material and then just sinter them afterwards. So it's a very rapid printing process. So smaller parts will be, I mean, cheaper, or the cost per part will be lower. But when we talk about the big parts, of course, I mean, 400 or 500 millimeter height or something like that, you know, half meter, then they will still be a little bit more costly compared to the small ones.
Thank you.
You are welcome. You are welcome. This is relatively speaking, you know, I don't think that we will be able to get a huge machine for 1,000 or 2,000 euros in near future. But considering that they were like $1 million or euro like 5-10 years back, now you can buy something for 200,000 euros. So that's, I mean, is a considerable amount of drop in the price, but not for, of course, end user. So still we are talking about huge companies which can invest in this technology, but they could barely buy one machine in 5 years. But now we just see in magazines where this news are posted regarding additive manufacturing, one company can buy 5 machines at once. So that is why it will be more accessible by companies, smaller companies. I hope I could answer your question. If there are no more questions, I will continue. Then in this part, I will talk a little bit about the types of metal forming processes. You will see more real-life pictures at least. Then I will show some application examples. So first, we distinguish metal forming into two types based on the surface area to volume value of the part. So bulk metal forming is the formation process resulting in massive shape change, and where we have relatively small surface area to volume ratio. So when we look at this circular rods or bars or slabs, then we are mostly talking about bulk metal forming. And here you can see a bunch of parts which can be named as bulk metal formed. And there are different types of processes. I will show examples for some of them. So when you hear about closed die forging, open die forging, extrusion, upsetting, hydroforming can be also related to sheet metal, but also for bulk as well. Orbital forging, rotary forging, ring rolling, profile rolling, coining, and micro forging. These all can be considered as bulk metal forming process. Sheet metal forming, on the other hand, is used when we have a part which has a high or big width and length compared to its thickness, and surface area to volume ratio much larger than the ones used in bulk metal forming. So there are some examples shown here, like bending or roll forming or deep throwing. These are all thin parts, relatively thin parts. And the processes that we consider here are a couple of examples. There are still much more, but these are the most common ones. Flat rolling, roll forming, bending, flanging, stamping, deep throwing, and stretch forming. And then we have another way to categorize these forming processes, where we say net shaping and near net shaping. So net shaping is a type of process where we have the final part out of the press. So you just forge it or form it, and then it is ready to be used without any secondary operation. Near net shape, though, is a process where the part requires a small amount of secondary operation, can be drilling, machining, some material removal, basically. And here you can see a couple of examples where the part is changed from a preform to near net shape. And when we get closer to the final geometry, and if we can produce it by forming, then we can save a lot of material by that modification. And material saving means money, especially for, I'm talking about, of course, industrial approach. So because when you waste material like scrap, you are basically throwing money away. So if you can get the same result by using less amount of material, you basically cut the cost and save money. And also you avoid some of the secondary operation to get the final part. And this another classification for forming based on temperature. Here we distinguish cold, warm, and hot based on the recrystallization temperature of the material. So if we do it under the recrystallization temperature, we name it as cold forming. If it is around slightly lower or higher than the recrystallization temperature, it is called warm. If it is quite away from higher than recrystallization temperature, we call it hot. So all these three types, they have their own advantages and disadvantages. On the cold side, we have high dimensional accuracy, high strength, as we talk about hardening, which comes from deformation. Surface quality is much better in cold condition than warm and hot. And we have, as we also mentioned, almost zero or very low scrap. And we can get net shape parts. But on the other hand, we have high forming forces and high die load, which means that the tool materials should be high quality and should be able to bear all the forming stresses. Therefore, the tooling cost can go up. So only small parts can be forged in cold condition because of the force you need to form it. So maybe less than half kilo or something like that. We need mostly multi-stage presses, which are quite expensive. We need tempering mostly before forging to soften the material and make it easier to change shape or deform. And we can reach a certain amount of deformation on the part. And when we go beyond it, the part will mostly crack or fail. If I just the right side, we talk about hot forging. It is a bit of opposite. We can produce complicated parts with complex geometries. Very big parts, maybe 100 kilos, 200 kilos, or something like that, can be produced by hot forging. High deformation degree is achievable. We can change the shape of the part much more than the cold condition. Die loads are relatively lower, I mean, compared to cold forming, and we don't need any tempering because we already heat the part. But opposite to cold forging, then we have some drawbacks in hot forging. We have scale formation. You know, this shell which forms on the outside of the part due to oxidation, and that causes quite a bad surface quality. Dimensional accuracy is much lower because of all the thermal effects, thermal expansion and contraction, which we observe during the process. We need to preheat the tools to prevent thermal fatigue and thermal shock. And we need very high temperature resistant tool materials. And warm forging is a bit of combination of these two in terms of both advantages and disadvantages. So sometimes we can keep the temperature lower for a part that can be hot forged, for instance. But we can just increase the dimensional accuracy and reduce the heating costs. But in some cases, for instance, if the part can be barely formed in cold condition, we can heat it up a little bit, up to 300-400 degrees. We sacrifice a little bit from dimensional accuracy, maybe from surface quality, but then we will be able to form it in an easier way on a low capacity press, and we can produce a part which cannot be produced in cold conditions. So warm forging is the backdoor to, it is the midpoint of these two ends of the different process types based on the temperature. And when we talk about the recrystallization temperature, it varies from material to material. If it's a carbon steel, it is 550 degrees average. If it is copper, it is 200. For lead, it can go even sub. So it is material dependent temperature. So when we hot forge a carbon steel, we go up to 1200, like 1200 degrees. But for aluminium, 650 degrees means hot forging. And recrystallization temperature depends on the degree of deformation. So when you deform the part, the recrystallization temperature also change. And when we look at the dimensional accuracy, we can see at room temperature in cold condition, we can get very low surface roughnesses, there will be no decarbonization, even in warm forging towards the cold side, and achievable tolerances within microns. So when we increase the process temperature or part temperature to hot condition, then we, of course, get a rougher surface with higher surface roughness values, and there will be decarbonization with a considerable amount of depth, and the tolerances will be, achievable tolerances will be much higher, like plus minus 1 millimeter, depending on the size of the part. And here are some examples of the parts which are manufactured by using different materials. Steel is maybe the most common in automotive industry. For household equipments and for heating systems, for instance, where we have this fluid going inside, brass is used as a common material because it's also temperature resistance and corrosion resistance. Copper pure copper is mostly used for gold-like parts for appearance mostly, and also it might be necessary for electricity conduction. Aluminum is very popular due to lightweight, and it is becoming more and more popular in automotive industry, and we also see it in aviation. But when we need lightweight with strength, then we are switching to magnesium or titanium, which are much more expensive, but there we can get a good strength for low weight. You will also see some numbers here. When we look at the material properties, we see the lightest material among these four is the magnesium, and elastic module or stiffness is highest with steel, of course. But when we look at the specific strength, for instance, so tensile strength per density, here the titanium shows the best performance. And concerning indent strength or shell stiffness for sheet parts, again, these are the specific values, I mean per density values. Their magnesium is the best option to use there. Wheels on the cars. So magnesium material gives the best strength versus weight ratio. And I will show some part examples. I mean, all the parts that you see here are produced in cold condition. And here we can see bolts, nuts, some gears, and I'm trying to turn off my phone. Some gears, spiders, inner races, some nuts, pins, and as you can see, these are all rather small parts. The big ones here actually made of aluminium, which are shown in the middle. There we can go or produce a little bit bigger parts than steel or other metals, because there we need lower forces due to low flow stresses of the material. Here we have a little bit bigger parts which are forged in warm condition. Here the main thing is the dimensional accuracy. So it should be, of course, both producible on a press, and at the same time we try to get good surface quality and dimensional tolerance as much as possible. So by keeping the temperature as low as we can, it is possible to produce these parts. And for bigger parts and more complex geometries, as you can see here, these can only be forged in hot condition. So it's these at lower temperatures. So I will finally show different examples for different types of processes. This is maybe the most popular or well-known process type, closed-die forging with flash. More or less all the big metal forged parts are produced with this method. Here on the lower right part, you can see a die, upper and lower die. Of course, this is put on top of the other one of a crankshaft. And this is the production stages of the crankshaft, where we have a raw material, a pre-formed production, which is probably reducer rolled here. And then it is forged in multiple stages, and then this flash scrap is removed from the part. And the other one is an example of connecting rod, where two parts are forged at once. There's a different type of closed-die forging process, which is without flash. This is very difficult to design because you have an enclosed cavity and you have no room for excessive material. So everything should be point shot, it should be very well calculated, starting from the volume of the part. And when you cut the raw material, you should have the same volume for all the parts that you are going to forge. So if you have a little bit bigger raw material, it will create extreme forces or pressure on the die, and it will probably break it. So this is a very sensitive process, and numerical simulations is a must to use while designing such a high accuracy process. So here are some parts. These are hot forged, but without flash. These are examples of extrusion. There are different types again, like forward rod extrusion. This is a spider where we have lateral cup extrusion. So the press is pressing from top side, and these four arms are extruded or flow in lateral direction. I didn't put many videos because I don't know how the internet connection speed will be, but at the end I will give you a link so you can download a very nice video showing different process types, which is, I don't know, 10 minutes long or something like that, prepared by German forging group. So I advise you to watch it to get a better understanding of this process. So here on the right side, these are cups, which are produced by backward can extrusion process. These are helical gears, and these are hollow parts where the part is extruded again. And this a little bit academic study shows how far we can go with the lateral rod extrusion. So we just press from the top, and there is an opening in the die, so material just flows in the horizontal direction. So this is done in Stuttgart University. Another process type is rolling, hot profile rolling. Here we have rollers, at least two rollers, and a hot bar or a plate, which is fed into these rollers. And then while they are rotating, the part comes out in a certain shape, which is the negative form of the roller shape. So most of the parts you see here are rolled in several stages, so it's not done at once. So it goes from this roller and goes to another roller. It is deformed a little bit more and more. So mainly long profiles are produced by using this method. Ring rolling is a different way of rolling process. Here we produce seamless one single piece big rings. Again, there are some rollers here, but this time more than two. Some of them are, you know, idle rollers, guide rollers, axial rollers, and so on. And here, the one that I'm showing with the cursor, this one is moving towards the other one, squeezing the material while it is rotating. So decreasing the thickness and increasing the diameter. So that's how big seamless rings are being produced. This is the only slide where I have a video because I think it is a very unique process, and I don't know if you can see something like this in Turkey anywhere, because as far as I know, these machines are not used here. This is an axial forging process. This is used to produce like gears. We call them splines. These vertical teeth on a shaft, outside or inside, by axial forging. So the thing is that if you just take a press and put the part upright like this, and you just use a die with this negative shape of this spline, if you try to form it, it will buckle. So there will be no teeth here at the top. However, if we do this in a with an oscillating motion, you know, if the die moves back and forth at a certain rate and speed, this is slow motion, by the way. This is much faster in reality. It is possible to reduce the forces by up to 40%, and it is now possible to form the part, form these splines without any buckling. So this is a quite unique process, and there's a company called Fels in Germany producing these machines, and the company that I worked for, Strakon in Denmark, they were producing tools for those machines. So that's how I got familiar with this type of process. And this is another process type, similar, a little bit similar to axial forging, which is called rotated swaging. Here, these dies, they rotate in a space where there are certain rollers making these dies move back and forth again like a hammer. That's why it's called swaging. So while they are rotating, they squeeze the part, and that's how they form it. So with this method, it's possible to form these hollow shafts and reduce the diameter, and even it is possible to produce variable diameters, which is not possible to do by using another conventional forging method. So this is a little bit of, again, unique process type. Coining is also bulk metal forming process. You may think that it's a thin material, so it is sheet metal forming. But as I said, the ratio is important. I mean, not only the thickness, but also the relationship between the width and length of the part. So these parts, the other two dimensions of this part, so since this is a circular part, I'm talking about the diameter. Diameter is quite close to the thickness. So that's why this is not a sheet metal forming process anymore. This is a bulk metal forming process. And this is also done in cold condition. And micro forging. So this is a very high value added process. Not many companies can do it because tool manufacturing is extremely difficult. And on top of that, just imagine measuring the dimensions of that part after you produce it. So you need some special equipment to be able to measure all these diameters, lengths, radii, and so on the part. So even with a caliper, you cannot measure anything. So this is a very special type of process, and it's even though it looks simple, I mean, because the parts are small and you don't need much forces, believe me, it is much more difficult than forging a crankshaft which weighs 100 kilos. And if you look at the examples of sheet metal forming, we can start with a very basic process, flat rolling. Here we can have 2 rollers, 3 rollers, or these like tandem rollers where there are several supporting rollers are used to reduce deformation of the rollers during rolling to get a high accuracy strip out of the rolling line. So this is a typical sheet metal forming process. Roll forming is also a sheet rolling process, but here it's not flat anymore. We produce profiles, and this can be both quite simple like L or C shape, or you can get very complex profiles where you just bend the part in a way to lock it. And these production lines can have a length up to 30-40 meters because it requires several stations or steps to bend the sheet while rolling it. As I said, I didn't put many videos here, both because of time and due to potential lack of connection speed. So you can, if you just YouTube it and write roll forming, you will get maybe 10,000 videos showing this process. Deep drawing is also a very popular production method for sheet parts. Here we have a die, we have a punch, and we have a part holding the sheet material, which is called blank holder. So what happens? This punch pushes the sheet material into the die cavity, and then at the end you will get a hollow part with the same shape of the punch. And this can be repeated in several steps to produce complicated geometries. And even these sinks in our houses, they are also deep drawn. Bending, it looks quite simple. Again, and the punch and the die, you just bend it. But with this press brakes, it's possible to produce quite complicated profiles again by using this bending method. You just bend it several times in different angles. This is a rival of roll forming. These two processes can both produce profiles, but if the batch size is big, if you need 100 meters of the same profile, then roll forming is more cost effective. But if you need only 1 or 2 profiles parts, then bending is a much cheaper way to produce those profiles. Spinning and stretch forming, these are 2 special types of sheet metal forming processes. These stretch forming are used to bend very big sheets which cannot fit into a normal press. So there are some separate hydraulic systems moving the die and some clamps holding the sheet from the sides, and then it is formed or bent to have a nice curved shape. And spinning is used to produce again big circular parts and long parts which cannot be easily deep drawn. So what we do is we just put the sheet on a spindle, and now with a roller we just deform it to cover it cover the mandrel to have the same shape. So this is also a very tricky process, because if you push it too much, you can make the sheet material very thin, and you can even crack it. So you need a very, very good roller design and the process speed to be able to form this part while rotating at a very high speed. And this is the video that I named. You will get the presentation. So if you just copy and paste this link in a web browser, you will be able to download the video. And I think it will be very helpful to get some, live videos or showing the processes in a moving manner rather than pictures. Normally in a face-to-face course, I would show it and talk about it. But here, I just give it as a homework to you. And if you have any questions, then next week we can talk about it. So, any questions? Nothing? Okay. So next week, next Wednesday, same time, we will talk CAE, which is abbreviation of computer-aided engineering. Of course, this is not what we mean, but same thing, that I mean computers and robots helping engineers to make the work. And I will talk more about these colorful pictures, which is the numerical simulations, and which is the main tool that engineers are using today, not only in metal forming, but more or less in all areas of manufacturing and also product design. So we will go deeper in numerical simulations and computer-aided engineering next week. So thank you very much for listening to me. I hope I could give you some new information, and would be good to have some feedback. I don't know, shall I pick somebody from these 9 names that I see on my screen? I don't know, Akın Demir, for instance. Would you like to say something on behalf of your classmates? It's a blind shot.
Firstly, hi, and thank you very much for these informations. Actually, I'm interested about additive manufacturing and other kind of thing. Because of that, it was very good to me. Thank you very much.
You are welcome. So we just decided to, talk about metal forming in this lecture. Maybe in a separate time, I can talk quite a bit about additive manufacturing, if we can maybe later arrange a time period. So I would be happy to share, information, because the more we share, the more it gets. I'm talking about information, so it's quite important for me to give as much as possible. So I will just take it as a note and discuss it with my professor. So, and then maybe we can arrange another additional optional course where we can talk about additive manufacturing.
It's really good. Thank you very much.
Thank you. Thank you for your comments. So, anybody else? Emre Küçük? Somebody, another blind shot? I think he's not there.
Any question from the audience? No,
I wanna also appreciate your presentation. It was good for us because their info is presentable and good to know that. Appreciate that.
Thank you very much. I tried to do my best, so I'm glad that you managed to get something and I was able to explain it. I hope it wasn't that boring with some theoretical background information.
Okay.
So
Thank you
very much. Yeah, thank you for this opportunity and taking time to listen to me. And
Okay.
hope to see you all next week. Same time, same day, right?